So, hi folks, my name is Scott. I'm a software engineer at Espressif Systems, currently working on the Rust language enablement team. Espressif is mainly a hardware company, but hires 90% software engineers because most of the application of our processes uses a lot of software. I myself have been using Rust since 2018. I had an interesting start to learning Rust. I was currently working on a embedded C project at the time, and that was a nightmare. The memory safety issues were driving me up the wall. I then saw I can't remember if it was a Hacker News or Reddit thread about Rust. I was like, okay, this seems crazy good. I'll try it out. So just a pro tip for anyone, don't try and learn Rust on embedded. It's not a good idea. The constraints of embedded and how difficult Rust is to learn in the first place makes for a unfun experience. But I got through it, and I've been using Rust professionally for 4 years now, so I can safely say it is nice on embedded once you know Rust. So what I want to cover today is, firstly, what is an embedded system? Some of you might know what it is already, or some of you might not. Why you might want to use Rust for embedded systems, how async can play a role in embedded systems with Rust, and finally I'll talk a little bit about Espressif's offerings, both in terms of hardware offerings and the Rust support. So what is an embedded system? That's quite a hard thing to define because you'll find people working on embedded systems with various levels of capability.
I think it's at 8 o'clock. That's an embedded system.
Yeah, that's a good example of an embedded system right there.
Scott will now be rewriting it live. Yeah, sorry about that.
No worries.
That's an embedded system.
So the definition I've come to use is a system created with a specific purpose, in this case, opening and closing a window. Usually there are some real-time computing and resource constraints associated with this, and sometimes both. And what I mean by real-time is reacting to system events as quickly as possible. Although on your laptop it feels like when you touch the mouse you move it, especially under contention, that can take hundreds of milliseconds to actually respond to those events. In an embedded system, typically the timing deadlines are a lot shorter. In terms of resource constraints, you're going to have a lot less memory and a lot less CPU power available, sort of in the order of kilobytes of RAM instead of the gigabytes on modern computers, and tens of megahertz or maybe hundreds of megahertz CPU frequencies instead of the gigahertz and multiple cores and megabytes of cache that you have on modern PCs. And this is important because you need a language that can run fast on these smaller systems. The debugging and execution cycle is also different. So typically in an embedded system, there'll be some embedded flash memory actually on the system. Sometimes it's built into the CPU itself. And with this, when you build your program on your laptop, it somehow needs to get there. There's a couple of ways to do this. One of them might be a simple bootloader that the CPU runs at the start, almost like a BIOS, in which you can tell it to flash an application like that. Or often, and especially in the embedded Rust world, we use debuggers, and these are just essentially a communication transport between your laptop and the embedded system. And it allows you to poke memory, read register values back, even write your own code into RAM and execute it. So why Rust for embedded? I'm sure I don't have to convince you guys that we should be writing everything in Rust, but I'll go over the important points as to why Rust is really powerful for embedded. So as I spoke about in the intro, memory safety is an interesting one. Most embedded systems don't have an MMU, which is a memory management unit, and this means that when you run into memory safety issues, worst case, you're going to silently corrupt your program without ever knowing that it's been silently corrupted, and good luck debugging that. And best case is this memory unsafety somehow triggers a CPU fault. So, for example, you access something with the wrong alignment. Either way, when that happens, you're going to end up in the hard fault handler, and 9 times out of 10, especially if it's memory safety related, you're going to have to reset the chip and start again. This is because if you've ended up here with a random unaligned access, you don't know what's been written to. You may have just overwritten your kernel or something like that, so not good things. So having memory safety built into the language with no performance cost is really, really good. The other thing is the ownership model maps really cleanly to the physical world in an embedded device. So when you buy an embedded device, you choose what peripherals you want on this chip. There's only a limited amount, and we can treat these limited peripherals. So, for example, a SPI port, you may have 2 on this chip. If you just used a index to get, say, SPI 1 or SPI 2, that would be great. But if you then call it for SPI 3, you're going to have a problem. This also is really powerful for modeling buses. So buses are very common in embedded, where you might have to share a bus between multiple things on there. So you'll have, for example, the SPI bus again, you may have 3 different things on there, and obviously only one thing you can only talk to one thing on the bus at a time. Rust, like borrowing and lifetimes, allows us to virtually and at compile time ensure that we're using only one thing at a time, which is really powerful. I hope I never have to touch a makefile again. Cargo is just too good, and being able to pull in interface crates like the embedded HAL crate, and HAL is just hardware abstraction layer. So the SPI thing I was talking about earlier, it's just a communication protocol typically used in embedded systems. Inside the embedded HAL crate, there's an interface for what a typical SPI transaction or read or write transaction looks like. And it means that chip manufacturers like Espressif can implement the traits for their chips, and the drivers, so for example a display or a temperature sensor, can just use those traits to implement the communicating with that chip. And that means you can mix and match any hardware device like a display or temperature sensor with any CPU that or processor or HAL that uses these traits. It also means that we can pull in library crates like the heapless crate, and heapless provides vectors and queues and strings that we can either statically allocate or allocate on the stack. I'm pretty certain every embedded C project I've ever worked on, at some point someone rewrites a queue that's slightly broken in various different ways. So it's really nice to be able to just drop heapless into your cargo.toml, and you have a performant queue ready to go that's correct, most importantly. Speaking about debugging earlier, we also have the ProbeRS toolkit, and this is a community-driven effort to create a toolkit for interacting with embedded devices. And this means essentially communicating with those hardware debuggers and providing tools like there's profiling tools, there's logging tools, there's tools for creating a debugging session. There's even a VS Code extension, so you don't have to use GDB. You can use their, I think it uses the DAP protocol instead of GDB, which is really nice. And finally, we have the Wacom project. Wacom is not very known, but it's really cool, and you'll see some more of it later. One of the biggest things about embedded is that you actually need the physical device in front of you, and then you have to wire it up. And if you do make a mistake, chances are you may break something. It's pretty hard to break things these days, but there is a chance. With Wacom, you can simulate these systems in the browser, and there's even a VS Code extension, and it runs the exact same code that you would run on the hardware anyway. So that's really cool. Another really cool thing about Rust is that the built-in async and await syntax works on embedded systems, so it doesn't require alloc. There's no threads required. And using this, we can provide single-threaded concurrency where it wouldn't be possible. You'd have to bring in like a RTOS or something like that. This is really good for resource-constrained microcontrollers. So if you have very little RAM, if you bring in an OS, first of all, there's a cost with the OS. Secondly, you have to size your stacks appropriately, which is difficult, and usually you give a little bit of overhead per stack, and that overhead adds up over however many tasks you have. And the third point is probably the biggest point for me, is that you can write asynchronous code that has similar ergonomics and looks like synchronous code. So it's very easy to read, as I'll explain in a little bit. I'll just quickly go over how async works, just to show you how it works in embedded systems. This is by no means a async tutorial. There's much better resources than this, but you can essentially only await something that implements the future trait, and the future trait has one method, which is poll, and it's either going to return poll ready or poll pending, depending on whether the future is complete or not. When to poll is an interesting question. You obviously you could just poll it in a loop forever, but this is not a good idea because you're using 100% CPU. You can't do anything else. So ideally, we'd like to say, tell me when this thing is done. And this is where we introduce the concept of the Wacom. And the waker is something really simple. It's just a signal to say, hey, this future could be done. Poll it again, please. And waking a waker can happen from anywhere. This could be, for example, on a desktop system, a operating system callback to say there's some socket there's some data in a socket. It could be just another function. If you think about a async channel or a queue, if you know you've just sent something, then you can wake the receiver because you now know that something's in the channel or queue. But in many embedded cases, it'll be an interrupt handler. And an interrupt handler is just a hardware mechanism to respond to hardware events. So, for example, you may tell the CPU to watch this pin, and if the pin changes, interrupt and jump to this handler. So when the pin changes, the CPU will stop what it's doing, jump to this handler, and you can process the result there or come back. And in there you can call wake, and whatever was waiting on that future, it will now be polled again. A popular executor for embedded is the MC executor. MC actually has it's a whole project, like they have HALs for different chips and various utility crates, but just the executor itself is slightly different to probably what you've seen before with Tokyo or Async STD or stuff like that, in the fact that tasks are statically allocated. So whereas in Tokyo you can just spawn them on the fly, in MC the space required for the task is allocated statically. And this is done because in embedded, typically you want to avoid a allocator, not always, depending on how much memory, but definitely in a limited memory scenario, you're going to run into heap fragmentation quicker. It doesn't just mean that you can spawn one task. You can actually provide a capacity method to this task. So if you know you want a number of tasks, you can say, I want 3 tasks, it will reserve space for 3 tasks. So let's go through a super trivial embedded scenario. But as we've seen with the thing that opens the window, there are trivial embedded systems around, so I guess this is more relevant than I thought. So basically, we're just going to say, let's read the button, read the state of a pin connected to a button, so whether the button's been pressed or unpressed. And depending on whether that button is pressed or unpressed, we'll turn on or off a LED connected to a different pin. So if we look at the blocking example, so the first thing we see is a macro called entry. In this case, it's from the ESP RISC-V RT crate. And all this does is it sets up the CPU ready for executing user code. So by the time we get to main, everything's set up. When we're in main, we grab our 2 pins, we put the LED into an output mode because we're going to be either setting the LED high or low, and we put the button into a input mode because we're going to be reading the state of that pin. Then when we jump into the loop, we simply just check if the button is high. If the button is high, then we set the LED high, and if it's low, we set the LED low. This is super simple to understand what's going on, but we're using 100% CPU. We can't do anything else, we can't sleep, so we don't want to do this if we can avoid it. So let's try and use interrupts, as I've mentioned the interrupt handler before. So we have some more code. This time we define some globals. We have a mutex containing the button pin, and we have a state atomic, which is basically represents the virtual state of the LED. Sorry, the button. Again, we create our two pins. This time on the button though, we're going to listen for the falling edge and the rising edge events, and all that is falling edge is going from high to low, and rising edge is going from low to high. So in other words, button pressed, button unpressed. We then store the button in our global state, and we drop into the loop. This loop should look fairly similar, but instead of checking the button directly, we're now checking the virtual state and setting the LED there. By the time we get to this sleep line, program execution will actually stop here until an interrupt fires, so we won't go back to the loop until an interrupt fires. Which brings me on to the interrupt handler code itself. So say I press the button, we're going to jump into this code. The CPU will wake up and execute this handler. We grab our button from the global. We then clear the interrupt so we don't constantly call this function. In here we check the button state, so if it's high we then set the virtual state to high, or if it's low we set it to low, and then we exit the handler. At this point we'll be back into main code, and we were at the sleep line, but we've now executed, we've been woken up by that interrupt. We'll now start execution again at the top of the loop, and because the state's changed, we'll now set the LED to high. So this is really good. Oh yeah.
Do you take questions?
Yeah, go for it.
From the very little embedded Rust that I've dabbled with, you usually need to declare like a panic handler. Is that something you've omitted for brevity?
Yeah.
Can you repeat the question?
Yeah, so he mentioned that in embedded Rust, you need to register your own panic handler because there isn't one. Like when you use the standard library, you get a standard library panic handler for you. I have just omitted it because adding like all the code, I've omitted quite a few things from here and just trying to keep the important stuff because there's like a fair bit of setup that goes into a lot of these examples.
Okay, thanks.
But we have a crate. It's called ESP backtrace, and it will essentially it's specific to Espressif chips. But we have a panic handler that will also give you the backtrace. which isn't by default on embedded systems. So it's quite nice to actually have the backtrace there.
Cool, thanks for answering.
No worries. So with that with that interrupt example, we're leveraging the hardware. We're able to sleep, and we could even do other things in that loop before we go to sleep. However, it's quite hard to follow the flow of that code. I had to go back and forth between the interrupt handler and the main code. And it only works for hardware events. So for example, if you wanted to wait on a hardware event and say something coming through a channel, you couldn't do that at the same time. You'd end up blocking on waiting for the thing coming through the channel. So let's look at the async example, which is a lot more concise. So you'll notice a big difference is that now main is an async function. The macros changed slightly. We're now using the embassy executor, and it works the same way as Tokyo does, as in it just behind the scenes will set up the executor and then spawn a main task. We just pass the entry as the RISC-V entry, so it will call this for us. Again, we set up the two LEDs. We drop into the loop. And the main change here is that we now have button.waitForAnyEdge.await. And what this does is the exact same as the interrupt example. It will wait for the rising edge or the falling edge with an interrupt. However, because we're now using async and await, this function is paused here. So we now yield back to the executor. The executor can either choose to run other tasks or it can go to sleep. It has the context there to be able to make that decision. And because of that, you could wait for this button event and a async channel at the same time, which is really nice. So as you can see, it was structurally very similar to to the busy loop, but with async and await, we get that readability, but also the ability to run other tasks or go to sleep, which is really, really nice. Obviously, in this example, it's still using interrupts, but we didn't have to set them up. We don't have to look at the handler. It's all implemented within the HAL itself, which is really nice because users don't care about interrupts. Users don't care about this sort of thing. They just want to write code that's performant and works. So I have a small demo with Wacom. You can scan that and do it on your phone, or I'll show it in a second. You don't have to do it, but it should bring you to a Wacom page. And if you run the simulation, you should be able to press the button and the LED stays on whilst you're holding the button, and if it doesn't, it comes off. And hopefully you can also see in the serial console, if I pull this up now and run it, we have a second task spawned that just prints this little crabby guy. Hopefully you can see that. So if I
press F11, full screen.
Yeah, hold on. There you go. So we can quickly take a look at the code. This is just the exact snippet that that was in the slide, and this is the task that manages the button pressing. And as you can see, I can press it, hold it, let go, and no matter what I'm doing with the button, this still prints because we have a second task here that simply just prints this and then sleeps for 3 seconds and goes again. So in terms of what Espressif has to offer, we have RISC-V chips, the C series, the H series, and the P series. And going forward, we're almost exclusively going to be using RISC-V from now on. We also have some older extensor based variants, the original ESP32 and the S series. And almost all of our chips will come with Wi-Fi, Bluetooth, or a 802.15.4 radio, or all three in some cases. I think the C6 has all three. We also have, oh yeah, go on.
How is the bus support for extensor, or is it only good for basic 5?
I knew someone was going to ask me. It's getting better. No, it's quite good. We're still trying to upstream the extensor backend in LLVM, which is going a little bit slower than we thought it would. We have patches in review, but they take time to be reviewed, and extensors quite a closed down architecture, so there's not many open source experts on it, so trying to get other people to review it is quite difficult. But that said, it's making progress, and it's definitely usable. I rebased the Rust compiler on LLVM for each release. Now I've definitely seen a reduction in the amount of extensor related issues. But that said, there's still a few teething issues, but I know of companies using the extensor based thing and Rust, so it's good enough. With that said, use RISC-V. Across our lineup, we have both single core and dual core options. And on the newer chips, there's actually a kind of a secret third core. Most of them come with a small RISC-V ultra low power core that can handle some stuff when the main processor's in deep sleep. In terms of our Rust support, yeah.
How's the dual core offerings together with Embassy? Is there any support there at all? Or?
Yeah, just last week we had a community contributor add support for running. There's no support for running one executor that works on both cores, but there's now support for running individual executors on each core, and they can wake each other up. So if you have a channel on one core, if you have a channel with a receiver on one core and a sender on the other core, even if the other core's asleep and you send something over the channel, it'll wake the other core up, which is really cool. Yeah. So in terms of our Rust offerings, we have the more traditional Rust embedded, no SCD approach. All of this is under the ESPRS organization. I'm just hand-picking a couple of repos because we have like 40 repos under there. So ESP-HAL is probably the biggest one. It has all the support for essentially the peripheral drivers on the CPU, so the driver for using SPI, UART, things like that. ESP Wi-Fi is the next biggest one, and that adds, as it says in its name, Wi-Fi support, but also Bluetooth support. And finally, we have a separate repo for the IEEE radio driver. This is because most of this is open source. With the Wi-Fi, we still have some blobs that we use instead. If I had more time, I would have loved to speak more about it. Oh, yeah, go on.
Just for completion, is there any specific reason why Wi-Fi and Bluetooth drivers are in the same repo? Or?
It's because they're heavily coupled in the sense that they use the same radio frequency, they use the same radio. Like, it would be a lot of effort to separate the two, so we treat them in the same repo. Yeah. It also there's also a coex mode, so they can coexist, and trying to implement coexistence where they're in two separate places would be extremely difficult. So bundling it together, maybe we should rename the repo, but at this point I think it's probably here to stay. So this is something that's really cool. So I've been talking mainly about embedded Rust in the no STD support, but we also, I believe, we're the only we're the only silicon vendor that offers Rust standard library support. And this is built on the C-based ESP-IDF. And ESP-IDF exposes enough of a newlib environment to actually build the Rust standard library on top of it. And this is really cool because if you know Rust, jumping to embedded Rust can be quite daunting. Like usually you won't have an allocator, usually you won't have threads, whereas being able to support the standard library means that you can port your knowledge across quite easily. And we've actually upstreamed this port already, so if you just download a nightly RISC-V toolchain and use the build STD option, it's all there upstream, so there's nothing to be done there. Just a couple of weeks ago, we got, I think, I forget the number of the release, but I believe the latest Tokyo, as of now, will now actually run on the standard library port, which is really cool. So you can actually use Tokyo on an ESP, which is awesome. We also have a Rust-based development kit, and it's the one I have here that runs the example earlier. So if I press this button, it turns on. If I hold it, it doesn't. This is a very simple application for something as powerful as that, but that's got like Wi-Fi and Bluetooth on it and things, and I'm just turning on an LED. And with that board, we worked with Ferris Systems to create a training. The original training was based around using the standard library and that series of crates, and we've also ported a version using no STD crates using the same materials that Ferris provided. So if you want to go use the STD approach, you can, and also same for no STD. And if you know nothing about embedded at all, I can always recommend the Rust Embedded book. It's a really good book for sort of cementing the foundations of what Rust Embedded is trying to do. And with that concludes my talk. So, any questions? Yes.
What does it take to bring like a project like Tokyo on an embedded device?
As of now, you should just be able to copy and paste the Tokyo thing in your cargo.toml, and it should just work. The reason why it didn't work was I forget the exact reasons. There was a few things. So some lower level libraries needed ESP-IDF, the OS support for like sockets and things like that. And yeah, I think there was just a few other smaller things like that that prevented it from working, but now it works, so go nuts.
Tokyo can run without the standard library?
Sorry, Tokyo can run only with the standard library port. So we essentially have two different approaches, and I wish I could have spoke more about this, but we have the traditional Rust embedded way is no STD, like no threads, nothing like that, and that's what I spoke about for most of this talk. And at the end, we also have a standard library port which brings everything back, so you get threads, allocator, and things like that. And on that standard library port, you can run Tokyo and things like that.
And how do you do like this port in the standard library? You make Sargo or something?
Sorry, could you just repeat that?
Like you build the standard library for your real target?
Yes. So there's a unstable feature of Cargo called build STD, and it allows you to actually just build both the core library, alloc, and the standard library from source.
It's like the Z flag?
Yeah, that's the one. Yeah.
Yeah.
the embassy executor, async executor didn't have support for multicore. I know that if you use Tokyo, it automatically spreads across multiple threads, but can you do the same with embassy?
Yeah. So it depends on. So by default, embassy is single core only, but for chips that have more than one core, so there's some Espressif chips. There's also the I forget the name of it, RP2040, the Raspberry Pi thing. That also has 2 cores, so I believe there's a modified version of the executor that allows multi-core access. So Embassy's executor is structured in a quite a cool way. The core executor code can be wrapped in essentially a HAL layer, and this means that you can take all the work that Embassy have done to create the executor, pull it into your package and make some tweaks to it, and using that we've added like multi-core support for our chips. Yeah.
I was actually a little bit, I don't have any experience with embedded development, but I was a little bit surprised that there was an executor for async on embedded. How mature is this embassy? Because async is rather young in even just normal Rust, right? And still there are features being developed. Async traits are coming up. And so for embedded, how mature is it?
Repeat the question for the recording.
Yeah, so he was just asking about the maturity of async and the fact that a executor exists for embedded, like how mature is it and how usable it is. It definitely is new. So Embassy, I think, has been around for I think just under 2 years. I could be wrong about that. With that said, though, it's very stable and very usable, in my experience anyway. Most of the kinks of async, at least for embedded, have been worked out. So at the beginning, when async and await was first stabilized in Rust, it needed thread local storage, which meant that using it on an embedded device was a no-go, basically. But that's since been removed, and it's now very usable on embedded. In terms of not having async, I forget the name of the feature, but the one you mentioned about async in traits, that's an annoying one for sure. So I mentioned embedded HAL earlier. We also have embedded HAL async, but because we don't currently have async in traits, it means that crate will be unstable until we get that. Fingers crossed this year we will get async functions in traits, but we will see on that one. But in terms of usability, I think it's more than stable. I know people and companies that are building products based around this, and the founder and the main contributor to Embassy uses Embassy in his company, so it's very good.
Embassy still relies on a few unstable features, right?
The only one now is async functions in traits, I believe. It might need trait alias in impulse or it might need that one, but I think there's a new RFC to simplify that just down to the bits that MC needs, so hopefully that gets approved and merged, and then we won't need that either, because I think there's some issues with the implementation of that at the moment.
I believe the async traits are getting stabilized in 1.74.
Yeah. So 2 releases, yeah.
Nice.
Yeah. Yeah.
Like no standard versus standard, what's the size difference and performance difference?
That's a good question. So he was asking about the difference between no STD and standard library. What kind of code size and performance hit are you going to take? Performance-wise, I would say they work similarly. you're going to be limited by the power of the chip, really, more than anything. In terms of code size, I'd say the STD approach definitely has a bigger code size, pulling in the whole STD, and also you have to build the ESP ID IDF underneath to run the STD. It means that you end up with bigger binary sizes. For Espressif chips, it doesn't really matter. Like most of our chips come with like 4 megabytes of flash. So, I mean, I know that's not, not a massive number, but to us embedded developers, that's like, whoa. So it's not a huge deal. So, but yeah, the STD approach is definitely has bigger binaries.
To put that size in comparison, there are embedded chips with 128
Yeah.
bytes of RAM
Yeah,
and like 2 kilobytes of flash.
yeah. So 4 megabytes, whoa. Yeah.
What are some features that are like what makes an ESP chip particularly great? I think Wi-Fi and Bluetooth is somewhat defining, but is there anything else?
I think you're right that Bluetooth, Wi-Fi, like connectivity has historically been our main selling point. We've been like a leader in the IoT area for a while. I also think that, and this was particularly exacerbated by the chip shortage, that we also just offer a lot for your money in comparison. So when I was talking about the 4 megabytes of flash and the various amounts of RAM, you actually just get quite a lot of power, like raw power, for the money compared to other silicon vendors. So I'd say that's another unique point about Espressif.
Rust.
And Rust support, obviously.
Right.
What does a chip cost?
It depends on volume and all kinds of things, but they're comparatively cheap compared to competitors. Is that?
I think that's big enough.
Yeah, I don't want to get in trouble here.
In my experience, you can get relatively decent, like similarly sized to the RP2040 development boards / kits for 50 to 70 crowns.
Okay.
Yeah.
Since you have a Wi-Fi chip on most of your boards, can
Yeah.
I do HTTP?
Yes.
Okay. That's nice.
There is there's a couple of HTTP both clients and server crates. There's MQTT clients, and this is all stuff that because of cargo we haven't had to write. We can just pull it in. One of the examples I'm doing in another talk later on in the year, we'll be using an MQTT client to post data and read from a temperature sensor and post that. So it's really nice. Yeah.
Does Espressif also, is it only ESP boards, or do you also have support for STM32 boards and stuff like that?
It's just ESP boards. That's the ones we sell, so we don't want to do other people's work.
Can I ask more questions?
Yeah, go for it.
How far down the stack is the Wi-Fi driver open?
The Wi-Fi driver is quite closed. I think the highest level layer that you could implement yourself or using some other open source library would be the WPA part. The Phi stuff and all the firmware and things is quite closed down. But for example, the 802.15.4 driver is basically 95% open source. There's only one small blob to initialize the Phi, and that's it. So the rest of it, like the Mac layer and everything like that, you can write your own software for.
Is there a technical or legal reason to have that 5% locked out?
I don't actually know for that one. I know for the Wi-Fi it's legal reason, but for the 802.15.4 I don't know why that 5% exists in blob form. I'll have to look that up or ask someone.
What's the legal reason for the Wi-Fi?
That's beyond my pay grade, unfortunately.
I think that was it.
Let's give Scott a big hand.
Congratulations.